In Unit 5, we're going to talk about rational functions. And just so you have an idea of what it is that we're learning about, we're going to look at a function that's made of a fraction of polynomials, basically. So it's going to be something like y equals, or f of x equals, one polynomial over another. So now that we know all about polynomials, we're going to put them together and divide them out to make one final function. Now, a rational function has a bunch of different parts that we're going to be finding in this first video. So we'll be looking at the zeros, the y-intercepts, vertical asymptotes, horizontal asymptotes, and slant asymptotes. And I really should add to this list holes because I did not include it on the list. So let's add that to our list. Okay, so first I want to take a look at what does a rational function look like when we graph it. This is an example of a single rational function. These three red pieces of the graph make up the function. So it's not just a simple curve, it's a series of curves all put together. You can see in this case we've got an orange dotted line. That would be a horizontal asymptote. We've got two vertical dotted lines. Those would be vertical asymptotes. And then this function even has a little circle here, which we would call the hole in the function. Okay, so those are some of the different parts that we'll be finding. So back to the notes. When we look at a rational function and we want to find all these pieces, the first thing I want you to do is factor it. And I'll show you why. So factor first. So I'm going to go back to my graph. I'm going to pull over two versions of the function. So the first version of the function is a big, messy cubic divided by a cubic. Okay, so that's what the original function would look like. But then the second line is the exact same function, it's just in terms of factors instead. So our first goal will be to factor this thing. I'm going to turn that one on, that one off. You don't even see a difference because it's the same thing. Okay, so just in looking at the different pieces, we said that there was a horizontal asymptote. Looks like it's at about a half. So we'll be looking at our functions and trying to figure out where that horizontal asymptote is. We have a vertical asymptote at -6 and -1. So we'll be trying to correlate that to the function. We've got a hole at 1. So once we see the factored form of our function, it's going to be easier to pick out the different pieces of it. Okay, so let's go back to how to find the holes. Now, if you remember the function, I keep switching back and forth, sorry. The function had a hole at 1. And the thing that creates this hole at 1 is that both the numerator and the denominator have a factor of x minus 1. So wouldn't you think if we have a common factor, top and bottom, that it would cancel? And if you're thinking that, you're right. That would cancel out. So any factor that would cancel out of both top and bottom is going to create the hole. So I'm going to say created by canceled factors. Okay, so any factor that's common to top and bottom that you would cancel out, that's going to create the hole. So we would set that factor equal to 0, and that's where we're going to find the x value of it. Okay, so the hole was at, if I zoom in, the hole was at x equals 1, and it was x minus 1 that we were canceling out. Okay, next piece of the function, vertical asymptotes. So going back to my graph, we had, whoa, where is it? There it is. We had a vertical asymptote at -6. We had a vertical asymptote at -1. Now remember, the x minus 1 is really gone. It's been canceled out. Do you see that the factors in the denominator are x plus 6 and x plus 1? Those values are the ones that are creating those vertical asymptotes. Okay, so vertical asymptotes we will find by setting the denominator factors equal to 0 and solving. So I'm just going to put, I'll go ahead and write it out. Denominator equal to 0. Okay, remember in a fraction, a denominator can never be 0, or the function, a value doesn't exist when a denominator is 0. So that's where those vertical asymptotes are coming from. Our function will never have values where there's a vertical asymptote. And that's because those are the values that are zeros in the denominator. Okay, so holes come from the canceled. Vertical asymptotes are coming from whatever is remaining in the denominator as factors. Now let's talk about horizontal asymptotes. So that's the orange guy. That orange line has a value at a half. And you can see we don't have any factors here that would actually equal a half. So horizontal asymptotes come from a different place. There's actually 3 options in finding a horizontal asymptote. And those 3 options are decided by comparing the degrees of the numerator and the denominator. And remember, by degrees, we're talking about those biggest exponents. So if it's x squared over x squared, or x to the third over x to the second, or whatever, we're looking at those degrees. And as we're comparing these two values, there's 3 options. First option is that the numerator degree is the same as the denominator degree. Okay, maybe you have something like an x squared over an x squared, etc., with other terms added on, of course. If that is true, and I think that's what happened in this function here, right? And looking at our original degree, I can see it's an x to the third over x to the third. Or if I were to look at my factored out form, I've got an x to the third because there's 3 x's, or an x to the third on the bottom because there's 3 x's. Even if I cancel out that common factor, those degrees still stay the same. So consider those degrees. Hey, they're the same. We have a horizontal asymptote at a half. The half comes from the coefficients of those leading terms. So if the degrees are the same, we're going to pull the coefficients of the leading terms as our horizontal asymptote. So I'm going to say HA is y equals the coefficient over the coefficient. That is if the degrees are the same. So if they're both square, both cube, both fourth, whatever. Option number 2, the numerator degree is bigger than the denominator degree. So maybe this time it's like an x to the third plus stuff over x squared plus stuff. Top degree is bigger than the bottom. If that happens, then there is no horizontal asymptote. We don't have to worry about it. You can just say none. Option number 3 is numerator degree is smaller than denominator. So if we flip-flop that, make it something like x squared over x to the third with your remaining terms. When that happens, the horizontal asymptote will be located at y equals 0. Okay, so 2 asymptotes so far. First one was vertical. That was the denominator equal to 0. Second one, horizontal. That's when we're going to compare the degrees and have those 3 options. The other type of asymptote that we'll be looking at is a slant asymptote. So as opposed to having a vertical or horizontal line, we have a slanted line, which means we've got some sort of slope. Y equals 2x plus 5, y equals 3x minus 1, whatever it is. We have very few circumstances in which there actually is a slant asymptote. They only occur when the top degree, I'm going to say top, I'm going to say numerator. The numerator degree is 1 more than the denominator degree. So it's that case when it's x to the third over x squared plus whatever. Okay, that's when we would have a slant asymptote. Now, if you think back just a second, if the numerator degree is bigger than the denominator, there's no horizontal. If it's 1 bigger, that's when we have a slant. So you will never have both a horizontal and a slant. You can't have both conditions at the same time. Now, to actually find that slant asymptote, we get to do everybody's favorite move, which is division. So we're actually going to divide the numerator by the denominator. If you're lucky, you'll get to do some synthetic division because maybe the denominator is just x minus 5. Then you can do synthetic division. If it's something like an x cubed over an x squared, you're probably going to have to do some long division. Okay? But either way, slant asymptote will take the numerator divided by denominator. Zeros. We've talked a lot about zeros with polynomials. The zeros of a rational function are going to come from those numerator factors. So this is when we're going to take the numerator of our polynomial and set it equal to 0. So whatever factors you have in the numerator equal to 0 should give you your zeros. I'm going to go back to my graph. So in looking at my function here, we said the x minus 1 created the whole, so we'll just kind of ignore it. but the numerator also has an x minus 3 and an x plus 2. And if you look at your function, we have a 0 on the function at negative 2. We have another 0 for the function at 3. So those are coming straight from those numerator degrees. And then the last thing that we'll be finding for our functions are the y-intercepts. And again, just like with our polynomials, we find a y-intercept by setting x equal to 0. Okay, so those are pretty much the same thing. Zeros are going to come from the factors in the numerators. The y-intercepts are going to be coming from when x equals 0. So I'm going to go back to my graph. We'll see if we can find those y-intercepts. It looks like the y-intercept should be at 0, negative a half. Okay, so whether you go to the factored out form and plug in 0 there, or whether you go to that function that was in standard form and plug in 0, I always like the standard form because all the x's just turn into zeros. And all I have left is a 6 in the numerator. All those go to 0, negative 12 in the denominator, and 6 over negative 12 is that y-intercept. Okay, so just another quick rundown. Wholes find first. After you have factored, anything that cancels will create a whole. Vertical asymptotes come from those denominator factors. Horizontal asymptotes, we have to look at the degrees and think about which condition is true based on the degrees of the top and the bottom. Slant asymptote, only when the numerator degree is one more, we'll actually have to do that division. Zeros are going to come from the numerator, and x-intercepts from x equals 0. Okay, we're going to do one example here because we'll probably do the rest in class. So let's see if we can take these pieces of a function and actually create a function that has those. So I know I'm going to go ahead and say y equals, or f of x equals, and I'm just going to create a rational function. And for most problems, I don't mind if you leave things factored. It's easier to work with. We don't need to take the time to multiply it all out. Okay, so let's not even worry about that. So we have been given two pieces of the function. We have vertical asymptotes and we have zeros. Now remember, vertical asymptotes come from the denominator factors. So if there's an asymptote at x equals negative 2, that means there was a factor in the denominator that had negative 2 as a solution. So how about an x plus 2 in the denominator? Same thing with the 1. If there's a vertical asymptote at 1, that means there was a factor in the denominator that must have been x minus 1. Okay, so we can take care of the vertical asymptotes. The zeros of our function come from the numerator. Those are those factors in the numerator. So same idea. If there's a 0 at 5, that means there was a factor in the numerator that would have had 5 as a solution. So how about x minus 5? And then another one for negative 3 means there must have been an x plus 3. Now we could throw in some extra coefficients. We could throw in maybe a whole something else, but this is the basic rational function that has those characteristics.